Welcome back. So in the previous lecture we had defined the complex derivative holomorphic functions and related its equivalents with Cauchy-Riemann equations. In the coming lectures, that is this lecture and next lecture, we are going to relate the harmonic functions with holomorphic functions. So as a starter in this lecture we are going to uh, look at the Laplace operator, its properties and the harmonic functions. So the first thing about the Laplace operator is that it commutes with the translation operator. That is, it is invariant under translation. So the n-dimensional Laplacian operator is the sum of all the second order partial derivatives with respect to each direction. One can imagine the Laplace operator as the trace of the Hessian matrix, right? So Hessian matrix is the n cross n matrix, that is the collection of all possible second order derivatives. So there are actually n square second order derivatives, right? When you are in Rn, like for gradient. So if you are in n dimension, you have n first order derivatives, which is the gradient operator. You have n square second order operators. You have n cube third order operators, and you have n power k kth order partial derivatives. All these are so Hessian matrix is the second order partial derivatives. So the trace of that matrix is the Laplace operator, which is given here. So one can imagine the Laplace operator as a map from the space of all twice differentiable functions, continuously differentiable, to the space of all continuous functions. So when we say C2 or Ck, what we mean is that the kth derivative, or in this case the second derivative, is also continuous. Okay. So Laplacian is a linear operator from C2 to C omega. One can see the map like that, which means it will take a function defined on omega. So say a real valued function from omega to r, which is twice differentiable. So u in C2 omega. Laplacian will take it to a continuous function, right? Because Laplacian is the second order operator, so it acts on a C2 function and will give you a continuous function. Now for each element in Rn or each vector in Rn, one can define what is called this translation operator on the space of continuous functions. How do you define that? So T of T, so once you fix a vector A, so you are going to translate by the vector A. So the translation operator corresponding to the vector A is that it acts on a U, and it's the value of U where the argument is translated by the vector A. So this is the translation operator. So you take a continuous function U, TAU is also a continuous function. The way it's defined is like this. So it's basically it's same as U, except that the value of U, the value at x is the value of U at x plus A. So the nice property about Laplace operator is that it commutes with the translation operator in this sense. That is, the composition with the translation operator commutes. So what does this mean? Okay, let's look at a proof. So let's look at what is the derivative of the translation of a function. So if you take a C2 function, u in C2, so then the xth partial derivative of TA of u is the xth partial derivative of u at x plus a. Right? This is just by the usual derivative, the composition or the chain rule. Similarly, the second order derivative is the second order derivative of u at x plus a. So in that sense, Laplace composed with TA is precisely this operator, that is Laplacian of the translated or function. So Laplacian of the translated function, if you use this information that we have derived here, which is the second derivative of the translated function, is nothing but the second derivative of the translation at x. So this is precisely by this computation Laplacian uxa, and this is precisely the translation of Laplacian u, right? By this definition, Laplacian ux plus a is nothing but the translation of Laplacian u, which is Ta composed with Laplacian. So Laplacian commutes with translation. The other property about Laplacian is that it also commutes with rotation, right? So you see, this is so if you remember the lecture about visualizing complex numbers and maps, we had talked about how complex numbers can be associated with rotations and dilations, right? And in this talk we are going to relate some functions with harmonic functions, right? So these are all connected in the sense that you see Laplacian also commutes with rotations. Complex number multiplying by complex number is a notion of rotation and dilation, and every complex linear map is actually a rotation and translation, right? So these connections we have pointed out. So Laplace has this property that Laplace also commutes with rotation. So what's a rotation matrix? Just to recall, any orthogonal n cross n matrix. What is orthogonal matrix? Orthogonal means O, the matrix and its transpose multiplied with its transpose is the identity matrix, which means the inverse of the matrix is the transpose of the matrix. Such matrices are called orthogonal matrices. So you can talk of an n cross an orthogonal matrix, right? So given any orthogonal matrix, one can define this rotation operator on the space of continuous functions. That is, you take a function u which is continuous, then r of u is nothing but the value of u after the vector x is rotated by the orthogonal matrix. Okay, so this is the rotation matrix. Laplace commutes with the rotation matrix. Let's look at a proof of this. So to start with, let's uh, so let's fix y as a variable, or which is the rotation of the vector x. So if you take an x, if you rotate it using this matrix O, then the new vector after rotation, let's call it as y. So what are the components of this y? So it is the component of this ox, right? So yj is nothing but this. This is precisely the matrix operated on x and the jth component of that. Okay, so I is the column here, and summation is over I. I is the column of the O matrix, and summation is over I. This is the jth element of y. Now let's compute the partial derivative of Ru. That is, if you take a u, after you apply Ru, what is the partial derivative of this? So the partial derivative of this, so Ru is precisely u of Ox, which is u of y. So when you say Ru of x, it basically means u of y. So what is the xi derivative of u of y? So by chain rule, it is the yjth derivative of u and the xi derivative of yj summed over all j. This is just by chain rule, right? And in this case yj is precisely what we have given here. So the xi derivative of that is just the ith element in this sum, right? The rest of the things will xi derivative will be 0, so only the ith term will survive in this sum. So what you have is precisely oji, and that is the xi derivative of Ru. From this, so this is the xi derivative of Ru. So from this we know the gradient of Ru, that is, you know the xi derivative for all I. So gradient of Ru is precisely the O transpose acting on the gradient of y, right? Because this is precisely the sum over j, this is precisely the ith element here. right? So the xith partial derivative is the ith element of O transpose acting on gradient of y. So gradient of this is precisely this. Now let's look at the proof of this commutation with rotation operator. So you start with Laplacian Rux, right? So Laplacian composed with Rux, which is Laplacian of Ru. Ru is Ox, which is Ru is Uox, which is Uy. And we had said that Laplace operator is nothing but the trace of the Hessian matrix. So this is precisely the trace of the Hessian matrix acting on u of y. Okay. Now in this term you use this formula that we derived, that is gradient of r of u is O transpose acting on gradient of grad y of u. So here you have the transpose of that. So basically grad x of Ru. So Uox is Ru, but what you are doing is a transpose of that. So you apply transpose here and use that information. So what you get is the transpose of the quantity here, and the transpose of this is like AB transpose is B transpose B transpose A transpose, right? So the transpose of this is grad y u transpose and O, which is precisely what we have here. Okay. Now apply again. Now you see grad x is acting on this quantity, which means grad x of this is O transpose of this. So this, you use this expression again for this grad x of this. So you get O transpose of grad y acting on that quantity. But O transpose, you know, is identity, right? So this matrix is equivalent to this the matrix without O, that is just the Hessian matrix with respect to the y variable, and trace of that is precisely the Laplacian with respect to y variable. So Laplacian with respect to y variable, and this is precisely the rotation of the Laplacian. So Laplacian of rotation is same as rotation of the Laplacian. So Laplacian commutes with rotation. So one nice observation one can have with this property that Laplace commutes with rotation is that uh, if if u, which is a continuous function on omega, if this u is a radial function, right? What is a radial function in n dimension? You can think of any n dimension as the polar coordinates, right? N dimensional polar coordinate. What I mean is that there is a magnitude r and there is a theta coming from the unit sphere Sn minus 1. So so you can talk of a radial function, which basically means it's a function which depends only on, so ux is actually a function of mod x. Mod x is the magnitude of x. So it depends only on the mod x. It does not depend on rotation. I mean, so the function does not change on rotation. So that's a radial function. And since Laplacian commutes with rotation, it basically means that if you take a function which is invariant under rotation, then the image of that function under Laplacian is also a radial function. So basically the set of all radial functions is invariant under the Laplace operator. That is one observation that we can have immediately from this property that Laplacian commutes with rotation. So this is the property of the Laplace. So this is the Laplace operator, and the property of the Laplace operator that it commutes with both translation and rotation. And as I said, complex linear maps are precisely rotation and translation. Of course, complex, maybe when what we talked about complex map was in more or less, you can think of it as in R2 equivalent to R2 in 2 dimension. Here we have done these properties of Laplacian in actually in n dimension. Okay, so there is a nice connection between this in the case of 2 dimensions that we will see in the probably next lecture. But in this lecture, we are just setting up the environment. So what is an harmonic function? So an harmonic function is actually a twice differentiable function such that Laplacian of that function is 0. This is called an harmonic function. Okay. Um, so this actually came naturally after Newton discovered his um, gravitational, laws of gravitation and so on, and he wrote down the Newtonian gravitational potential. So the Newtonian gravitational potential can be given by this formula that it is the sum over the density and the distance. Um, so the value of the Newtonian gravitational potential at any point x is precisely the average of density over the distance from the point to every other material. So omega denotes the rigid body or whatever body we are studying about. So body in R3, let's say. So if omega denotes the region that we are interested in, and rho is the density of the material at every point y of the material or body, then you have this expression for Newtonian gravitational potential. Okay. So this was something that came out of Newton's work whenever he introduced his laws of gravitation and so on. So almost a century later, Laplace discovered that the Newton gravitational potential is a harmonic function in the complement of the body, that is outside the body. The gravitational potential is a harmonic function. Okay. So this is the complement of the closure, complement of the closure of the material. That is, this is an open set, right? This is the PD on the open set here. So it's so Laplace figured out that it's actually a harmonic function outside the body. In fact, today we call this as a Laplace operator because of that reason. Uh, and then almost another 40 years or so later, Poisson discovered that the Newton's gravitational potential, this U, is actually a solution of the Laplace operator with density as the given quantity on the right hand side as a data, which is why we call the inhomogeneous problem like this as a Poisson equation. Poisson equation. So here it's 0, here it's non-zero rho, right? This density. But in general, we call any equation of this form with right hand side non-zero as Poisson equation. So these were some property discovered about Newton's gravitational potential very soon, right? Within a span of a century and a half. So the motivation for harmonic function actually comes from interest comes from these kind of study. In fact, in physics, the all these are studied in the subject of potential theory. All these are analyzed in the potential theory branch. So let's understand what are harmonic functions. So let's look at what are 1D, one-dimensional harmonic function. One dimension means the space dimension is 1, which means the Laplace equation. So Laplace operator is just the second order differential operator, and the harmonic function definition becomes all u such that the second order derivatives are 0. Now in the one dimension, this is easy to solve. You have this fundamental theorem of calculus, right? So you just use that information, you integrate it once, depending on what, let's say you are in some domain, some interval AB. One dimension means you are in some interval AB. So you integrate it once, so you get a constant, that is the derivative of u is a constant. You integrate it once more, you get a 1 degree polynomial, right? So you can see that ax plus b, all these linear functions, all these lines in R2 are solution to are actually harmonic functions in one dimension. Converse is also true in the sense that uh, any function of this form is an harmonic function, and any solution to this equation is of this form, right? That we have already said. If you start with this equation, use fundamental, you just differentiate it twice, fundamental theorem of calculus, you get this equation. If you are given a function of this form, you differentiate it twice, you are going to get this equation. So basically, all the harmonic functions are actually given as the linear combination of the linearly independent polynomials 1 and x, that is the constant polynomial, and 1 degree polynomial. The linear combination of that is precisely the all the harmonic functions in one dimension. So one can classify the all the harmonic functions in one dimensions. What about the two dimensions? So in two dimensions, it turns out that you don't have such a simple result. Not just two dimensions, even in higher dimensions. Like let's take two dimension harmonic function definition, which is precisely this. That is the x second order x partial derivative and second order derivative with respect to the y variable is 0. All such functions. So like we did here, we can immediately check that any plane in R3 is a solution, is a harmonic function. So this is a 1 degree polynomial in two variables, right? So any plane in R3 is a solution to, is a harmonic function. But unlike the one dimension, where that is the all solutions are of this form, that is not true in two dimension. Because like there are functions like this xy is also a harmonic function that is not of this form. X square minus y square is also a harmonic function. Similarly, all these examples, x cube minus 3xy square, 3x square, y minus y cube, e power x sine y, e power x cos y, all these are harmonic functions in two dimension. And they cannot be put in this format always, right? So there are solutions which are not of this form, which are also harmonic functions. So it is different from the one dimensional case. So we have more equation. So is there a way to classify all the harmonic functions in two dimensions the way we did in one dimension? Okay, that's a natural question to ask. And that is where the complex analysis comes in play. That is, a complex functions comes in play, or the holomorphic functions comes in play. If you use the holomorphic functions, not exactly you classify, but you have a nice relation between all the two-dimensional harmonic functions and holomorphic functions. That we will see in the next lecture. Here we are just seeing the connections with Laplace operator and harmonic functions here. So the other uh, notion is the notion of Wirtinger derivatives. This is like the partial derivatives in complex functions. Now one would wonder, where is partial derivative coming in complex function? Because complex function was like one variable, right? That is, you have a derivative existence. So this notion actually came from the several variable complex function theory. But you also have a corresponding notion here. I am going to motivate these derivatives. So you see that if you take any complex function, which is usually a function given in terms of x and y, right? The real part and the imaginary part, real part x and imaginary part y. Basically, any z as a real part x and imaginary part y. And you know this relation that any real part can be written as z plus the conjugate over 2, and any imaginary part can be written as z minus its conjugate over 2y. So the real part is a function of z and z bar, and the imaginary part is a function of z and z bar, which means the x and y both can be written as function of z and z bar, which means any complex function which is given in terms of x and y can be rewritten in term as a function, as a two variable function, as a function of z and its conjugate, right? It's something which we can do. Now using this relation, now we we can observe that if you look at the partial derivative with respect to the x variable, and since x is a function of z and z bar, using chain rule, you can see that the partial derivative with respect to the x variable is nothing but the partial derivative with respect to the z variable and the x derivative of z. Similarly, z bar variable and the x derivative of z bar. And we know that since z is x plus iy, the x derivative of z is 1, the x derivative of z bar is 1. So this is precisely the partial derivative with respect to z summed with the partial derivative with respect to the conjugate of z. Same observation will tell you that the yth partial derivative by chain rule is this, which, because zy is now the derivative of z with respect to y variable is I, and this is minus I, so you get this. Okay, so this is a relation that we have between, if you write x, if you imagine x and y as a function of z and z bar. Using this, one can define the notion of, because now you have two equations, using this you can define the notion of partial derivative with respect to z variable and partial derivative with respect to z bar variable in terms of x, partial derivatives of x and y. So if you sum these two equations, then you see that you have del z here, you have I del z here. You can actually bring this I with the partial derivative of y. So you have this. So you can actually see that 2 del z is del x minus I del y, and 2 del z bar is del x plus I del y. This relation you obtain from the above relation. So one can define the partial derivative with respect to the z variable as 1 over 2 of this quantity, partial derivative with respect to the z bar variable as 1 over 2 of this quantity. And that's precisely what is called the Wirtinger derivatives. Wirtinger derivatives are precisely these derivatives, the partial derivative with respect to z and the partial derivative with respect to z bar, the conjugate variable. And now we can rewrite what we already know. We have already seen that any function is holomorphic if and only if it satisfies the Cauchy-Riemann equations. And Cauchy-Riemann equations written in this form, written in the Wirtinger derivative form, is precisely this. That is, the z bar derivative of f is 0, because the z bar derivative of f is 0 precisely means that the del x f and I del y f is 0. So if you write f, so if u and v are the real and imaginary part of this f, then what you have here is ux plus I vx. Similarly, here you have I vy plus I square, I uy plus I square vy. So, and that equal to 0 is precisely, if you equate the real and imaginary parts here, what you get is the Cauchy-Riemann equation. So Cauchy-Riemann equation is precisely the fact that the z bar derivative of f is 0. So any function is holomorphic if and only if it is independent of the z bar variable, which is why if when we looked at the examples, you would have noticed that z going to z bar, the conjugate function, was not a complex differentiable function except at z equal to 0. In fact, it was not a holomorphic function, right? So that is precisely because it's a function depending on z bar, so it's not holomorphic. Any holomorphic function should be independent of the z bar variable. It should not be explicitly dependent on the z bar variable. And any function is harmonic if and only if this double derivative, this mixed derivative of u is 0. That again you can quickly see, because what is Laplacian? Laplacian is del square xx plus del square yy, and that is precisely this. So if you say, if you multiply the RHS here and RHS here, what you get is the Laplace operator. So if you multiply that, what you get is 4 del z z bar. So the Laplace operator is precisely 4 times this mixed derivative, complex mixed derivative. So a function harmonic means Laplacian u equal to 0, which precisely means that 4 of this operator acting on u is 0, which is this which is this. So a function is harmonic if and only if this mixed derivative is 0. This is another way of looking at harmonic functions. And fine. Now let's connect the 2D Laplace operator with the wave equation. So you must have seen this wave equation in your PD course. If you have seen this one space dimension wave equation, like equation for vibrating string and so on, you will have a time variable and a space variable. So here if you think of x as the time variable and y as the space variable, or one can relate it like that. So now using this complex number I, the Laplace operator can be written as this operator, which is precisely, as I said, the product of what you have here and what you have here, a plus b, a minus b. So a square minus b square, which is precisely what you have here. Okay. So the Laplace operator can be written as this, and this can be thought of. This is a wave equation. This is in the form of wave equation, except that now the wave speed, right? The wave speed is now plus or minus I. So in general, what you would have seen in a PD course is that del t square minus c square or plus c square del x square, right? That's the kind of wave equation that you must have seen, one space dimension wave equation. So that c usually denotes the wave speed, the speed with which the wave is propagated. So in this case, the Laplace operator is actually, after you introduce the complex number I, you see there are so many advantages, right? We have already seen many advantages of introducing this complex number I. The other advantage is precisely the one here, that you can think of the Laplace operator as a complex wave equation. Okay. In fact, you would have also seen other advantages of the complex number I when you solve the second order constant coefficient ODEs, right? Constant coefficient ODEs, linear ODE in second order. You would have used the fact so you would write down an auxiliary equation in terms, and you solve that quadratic equation, and whenever that had complex roots, you actually have solutions in terms of cos and sine, right? All these. So if there were no complex number, you would not be so you would not have been able to solve those ordinary differential equation which actually admits real functions as solutions. But there is no way to obtain these real functions as solutions to those ODEs, like y square plus y equal to 0. If you take this, not y square, y double prime plus y equal to 0. If you take this ODE, if you try to solve it, you have to go through complex numbers to solve this ODE to get the real solution. You can actually check that equation y double prime plus y equal to 0 is the solution is spanned by sine and cos, sine x and cos x, right? It's span of these sine and cos, and these are real functions. So there are so many advantages of that, right? We have already seen. So since there is one more, I just wanted to point out at this stage. So the Laplace operator can be thought of as a complex wave operator. So in that sense, with the wave speed plus or minus I. And if you have seen the complex wave equation, you would know how to solve this, right? You would have seen that uh, the wave equation is actually a hyperbolic equation. There are two kinds of you can write them in two kinds if you know this canonical forms, writing the PD in their canonical form. For hyperbolic, there are two kinds, first kind and second kind. The first kind involves a mixed derivative, so you can actually have a change of variable in the wave equation. So if you have uh, t and x and c here, you can actually have this, or you can just say x, y and c here. You can actually have x plus cy as a change of variable, you can rewrite the wave equation as a mixed derivative, which is the first kind canonical form. And so now, since it's a mixed derivative, you can integrate it twice with respect to each variable. Then you will get a function of each variable in that as a general solution to wave equation. Something like that is what you have here. You see the Laplace equation is now written as a mixed derivative, but in the complex domain. In the real case, when you look at a wave equation, you have a mixed derivative in the xy variable. For Laplace, which is actually an elliptic equation. You see, that's the thing. When you do PDE, the Laplace operator is an elliptic equation. It's not an hyperbolic equation. The hyperbolic equation. But when you introduce complex numbers, you can think of this Laplace equation as a wave equation with complex speed and can be written as a mixed derivative in the complex derivatives. So in the case of real case, for a wave equation, you will have del xy of that wave equation solution equal to 0. So when you can integrate it once with respect to the x variable and then with respect to y variable, what you get is a function of x plus some function of y as a general solution. That is how you solve the wave equation, if you remember. In fact, if you remember the D'Alembert solution and other things, all these are obtained like that. There are many ways of approaching that. So if we adapt the same technique here, one can imagine that this complex wave equation has the general solution of this form, where the change of variable that you use is x plus iy and x minus iy, right? So that's the new. So if you use this change of variable, this can be written as a uh, this can be written as del z z bar as we have seen before. So z is this, z bar is this. So the solution that you're looking for is actually a function of z and z bar. And if you're looking for real solutions of the Laplace equation or harmonic functions, that means if u is real valued, then u and u conjugate should be same because it's real value, which means u is actually u plus u conjugate divided by half, right? So if you are seeking real solution, it is this. So this expression actually gives you. So if you take u bar here, it tells you it's the conjugate of the sum, right? So if you use this relation, you actually see that your real solution is nothing but the real part of this complex functions. Okay, so this is the connection that I wanted to give about Laplace operator and about harmonic functions. In the next lecture, we will, so in this lecture, we have seen only relating Laplace operator and so on, and we have seen how 2D Laplacian can be related with complex wave operator and so on. In the next lecture, we are going to relate harmonic functions and holomorphic functions. Okay, see you in the next lecture. Thanks a lot.